Bismillahirrahmanirrahim. Assalamu alaikum. I'm Fakhr Lodi and this is our 29th lecture of Formal Methods for Software Engineering. We have been discussing algebraic specifications. Remember that in algebraic specifications, we specify the behavior of the system in terms of the external interfaces that the system or the module supports. So what we have is we have abstract data types or the notion of abstract data types. And the abstract data type basically is that you have an abstract entity, and what you do is you specify the interface, you specify the methods that are supported by that abstract data type. So those are the operations that you can perform on it. Those are the queries that you can make on that particular data type. And then, the internal details are hidden. How this abstract data type is implemented, that part is hidden. So we only specify when we send a message to this entity, what will happen, how will that respond back, how will that react to that message, and what are the expected outcomes. So we saw a number of examples in algebraic specifications, and a couple of things that you need to remember and understand, that in algebraic specifications the most important tool perhaps is recursion. So we can specify our axioms, or we can specify the behavior of the operations when we write axioms, and one of the very important tools for writing those axioms is recursion. Then we started to look at some specific tools for developing algebraic specifications or supporting algebraic specification and developing systems from those algebraic specifications. So those algebraic specification languages, there are a number of such tools available, but we will be looking at only a couple of these. So first one that we started to look at is known as the large specification languages or set of languages. Larch was developed at MIT, and there are a number of specification languages. It's a family of specification languages that come under this general name of Larch. Larch has a two-tiered structure. Actually, there are more than two tiers in a program, but from a specification point of view, it has a two-tiered structure. The two tiers are, the first is what is your algebraic specification, and that is called trait in Larch. So trait is the algebraic specification of the abstract data type that we are developing. Then what we have is the interface. So the traits are written and developed in what is called Larch Shared Language, or LSL. And then we have a number of languages that we can use for writing the interfaces. The Larch Shared Language is independent of any implementation and technology. It is independent of any particular programming language. The Larch Interface Language, or the set of languages that we have there, those are very much dependent upon the programming language in which this abstract data type or this specification for which the program is to be written is going to be implemented. So we have interface languages for C, C++, Smalltalk, and many more languages. As I mentioned earlier, the large interface languages, or LILs, these are closely related with the implementation language in which you will actually develop your program. So idea really is that from specification to actual implementation, we should provide a phased approach. So this is kind of a stepping stone. So you step on this and then you move into the actual implementation. And here the data types and some of the other things that are supported by that language in which the implementation is to be finally done, that is what we have in this interface language. And finally, we take this implementation and then write the code based upon that interface in that particular language that we have. And so there is kind of a dependency, that is the actual implementation depends upon the specification written in the interface language, and the specification written in the interface language depends upon the specification written in the large shared language. The set of languages that we have seen, today we shall start with that. Last time we looked at one example of a trait or a specification written in a large shared language. That was the specification of a table. Today we shall see another specification, and then we shall see a corresponding specification in the interface language. Rather, we shall first look at the specification written in the interface language. I will talk about some of the characteristics there and some of the issues that we need to address, and then I'll show you the corresponding specification written in the large shared language. And then we shall discuss how the two are connected. So let us go back and look at the implementation, or look at the specification of this abstract data type written in the large interface language for programming language C. So this is known as LIC, large interface language for C. So this is the specification written for a queue or task queue in LIC, and see if you can make sense out of this thing. So here is the specification. We have uses task queue, mutable type queue, immutable type task. Then we have task star get task, and the parameters are queue and the variable name is queue itself. Then we have the body of this specification. It says modifies queue, ensures is empty queue hat, then result is equal to nil and unchanged queue, else star result dash is equal to first queue hat and queue dash is equal to tail queue hat. And then we have the end of the body of the task. Very briefly, I will go back and discuss the different aspects of this specification. But very briefly, you can see that the syntax resembles very closely with the syntax of the C programming language. We have the same mechanism for passing the parameters. We have this star which indicates a pointer, and so on and so forth. So it is the same way that we declare variables in C. There are obviously some new reserved words that have a specific meaning within this specification, but the look and feel, the structure is very, very similar to what we have in a C program. So this is what this large specification in C is. Now, what does that mean? Some of the concepts, actually, many of the concepts are very familiar concepts, although, once again, the syntax is slightly different here, but we have seen these concepts earlier on. So you should not have difficulty in understanding what is meant by all these different things. But let me, tell you what this thing is all about. As mentioned, the specification is written in LCL. This fragment introduces two abstract data types and a procedure for selecting a task from a task queue. Briefly, star means pointer to, as in C. Result refers to the value returned by the procedure. The symbol hat is used to refer to the value in the location when the procedure is called, and the symbol dash to refer to its value when the procedure returns. So first of all, the specification starts with this reserved word uses task queue. When it says uses task queue, so this uses means that it is using another specification written, and the name of the specification is task queue, and that specification would have been written in large shared language. So पहली बात तो ये है कि ये बता रहा है कि लार्ज शेयर्ड लैंग्वेज में ये स्पेसिफिकेशन जो लार्ज सी लैंग्वेज के लिए लिखी गई है, ये उस कौन सी स्पेसिफिकेशन से इसका ताल्लुक है. The second thing is that it is, introducing two abstract data types. One is the queue, the other one is the task. And then once again there are a couple of reserved words here, mutable and unmutable. Mutable means, when we say that this particular object is mutable, or an instance of this particular object is mutable, that means the code that we are going to write will change or update the value of that particular object. And when we say non-mutable or not mutable, that basically means that in that particular case, that particular object, the value will not be changed. It will not be modified. It will have the same value when the operation was called, and when we terminate the operation, during this whole cycle, the value of that particular object will not change. So queue is mutable and task is not mutable. That means we are going to update the value of queue, and we are not going to update the value of task in this particular operation. Then we have a couple of other things. Result means the return value. So we are talking about the result. When we say result, it means what is going to be returned from this method or function. Then we have this hat and slash or a hyphen. This hat means the original value when the method is called. So the value at that time when that method was called, that original value, जो हमारे पहले कॉन्सेप्ट में हमने old का लफ्ज़ यूज़ किया था in our other specifications, OCL and so on and so forth, ये उससे वही चीज़ मिलती जुलती है, actually वही चीज़ है. And when we have this hyphen with a variable name, that means, this is the value that is present when the function terminates or returns from this call. So completes its execution. So old value and the end result, all of those, they are represented by hat and this quote, single quote, and then at the same time the result variable, once again it is a reserved word. It means the return value, that is the value that is being returned from this particular function. Other than that, we have that star that meant the pointer, which is the same as we have in C, and the rest of the things, they were very, very similar to what we had in C. In this particular case, the specification of get task is not self-contained. For example, looking only at this specification, there is no way to know which task get task selects. Is it the one that has been in the queue the longest, or is it the one in queue with the highest priority? Now this specification, if you look at this specification, you look at the result. What is the result? Result gives you some task back. And what is that task? Which task does it return back? Question is it the task with the highest priority, or is it the task in that queue which is there for the longest duration of time? That is, we are not saying here whether we are implementing a FIFO queue or a priority queue or a mixture. So what kind of queue is it? It is not specified. From where will it get this information? This gets this information from, hopefully, from the specification written in the large shared language. This is where that information ought to be present, and if it is not present, obviously the implementation is free to choose whatever it wants, or whatever results it may want to show. So this is an important thing to remember, that specifications, they depend upon each other, and whatever has been written earlier on, that would be used here, and you cannot violate that contract. It is kind of contract that we have there, so you cannot violate that. Specifications are not limited to a fixed set of notations, but can use LSL to define specialized vocabularies suitable for particular interface specifications or classes of specifications. Now once again, here this is an important thing and a very useful thing. When you are writing a specification in the large interface language for that particular language for which you want to implement it ultimately, you may use other things to specify things. You may use another specification which is written in this interface language. But most probably, the most appropriate tool is the large shared language, in which those specifications which are independent of the implementation should have been written. Okay? Now, after having looked at this, let us now look at the corresponding specification in the large shared language. What does it look like? Although we have seen one example, but here I just want to show you, what does it look like. Here is the trait task queue. It includes natural, which is a natural number, task tuple of ID, which is of type natural, and important, which is of type bool. Introduces new, which gives us a queue. Then we have this sort of append or add operator, so which takes a task and a queue and it adds that task to the queue and gives us a new queue. Then we have is empty and has important, which take a queue and return a boolean. First takes a queue and returns the task. Tail takes a queue and returns the queue after chopping the head of the queue. So these are the signatures. This is what we have. Once again, there is nothing new here. The only thing here is that, maybe we are using a slightly different syntax than we are used to. But, other than that, this is exactly what we have been seeing and what we have observed and what we have looked at when we were developing algebraic specifications from a generic point of view. So there is nothing new here. Now, once again, let us look at the axioms. And, remember that in large, that body where the axioms are written starts with this keyword asserts. So these are the assertions that have to be fulfilled. So what are those assertions? Let us look at those assertions. So we have this Q, which is generated by new, and this add method. So these are the two constructor methods. And the assertions are for every T, which is a task, Q, which is a Q, is empty, new is true, is not is empty, T, when T is added to Q, that is also true. Not has important for a new Q, when the Q is just created, there is nothing that it contains, and hence it does not have any important task. Has important when T is added to Q is the same as saying T dot important or has important Q. That means that the task that is added here is an important task, or there is an important task which is already present in the queue. So then the queue would have an important task in it. First of T added to Q is equal to if T dot important or not has important Q, then T, else first of Q. And then we have tail when T is added to Q is equal to if first T added to Q is equal to T, then Q, else T added to tail of Q. यहाँ पर ये एक इंटरेस्टिंग चीज आ गई. जब हमने इसकी स्पेसिफिकेशन हमने बनाई, so in this specification what we are saying is that when we are adding a task, the task will have two things. One obviously is the task itself, and then there is an associated flag Boolean parameter which is associated with that task and which tells us whether this task is important or not. So when we are adding an important task to the queue, we will set that flag. So this is what the first thing is. Then there are simple things that we have talked about. Important thing to note here is that here, as long as there is no important task, it is a FIFO queue. But when there is an important task, that important task is added to the head of the queue. So in that particular case, it becomes a priority queue. So when you take that task, the first task that you take from the queue, it is the task that is at the head of the queue, and that task will be the one if it is there for a long duration of time, if there is no important task, or if there was an important task, then that task would be at the front of the queue. So ये important चीज़ है. So we are mixing priority queue and a normal FIFO queue here, and we are saying that if we get a priority task, a task which is important, we will put it at the head of the queue, and then when we take that, that is the task that we get. Now remember that when we were looking at the specification for LCL, this piece of information was missing there. But since LCL specification said that it was using the specification written in that shared language, and the name of the specification was given, and this is the specification that it was using, that now means that whatever has been written here must be obeyed by the specification and ultimate implementation. It cannot be violated. This is a contract, and the contract here says that we are going to add tasks according to their importance. If it is not important, then it will be added to the tail. If it is important, then it will be added to the head of the queue. And hence, we kind of make a priority queue out of this thing. So based on this information in this LSL specification, one can deduce that the task pointed to by the result of get task is the most recently inserted important task if such a task exists. Otherwise, it is the most recently inserted task. So, there is nothing very special about it, except that in this particular case, it is actually not a queue, but it is kind of a stack that we have. But the only thing that I wanted to show here, if you did not understand this particular point, just ignore it. That is not very important. But the important point, at this moment was that we wanted to just state that how the two specifications, they are linked together, and specifications or the constraints written or specified in one specification, how does that influence the other? So since the specification written in LCL is based upon the specification written in LSL, hence whatever we have written here, that serves as a constraint for the other specifications and ultimately for the implementation as well. So the third component of the large tool set is what is the large prover, or LP. Now when we write specifications in large, we would want to argue about those specifications, and when the designer or the specifier writes those specifications, the specifier makes certain claims about those specifications. What we want to do is we want to verify whether those claims are actually fulfilled or not by the specification itself. And that is given to us with the help of this large prover, which can be used at the time of debugging. We all know that it is not very easy to write the specifications. And just like any other thing, we can write specifications which are incomplete, inconsistent, or otherwise incorrect. We assume something, but it turns out to be something else. So this tool or this mechanism helps us in, first of all, identifying the error, telling us whether there was some problem, and then helps us in debugging the specifications. So what are those? Let us go back to the slide and look at the definition of those things. While some large specifications can be executed, most of them cannot. And to make it possible to validate specifications before implementing or executing them, large permits specifiers to make assertions about specifications that are intended to be redundant. These assertions can be checked mechanically, and there are several tools that assist specifiers in checking these assertions as they debug specifications that are already in use. Now there are a couple of things that we have said here. Number one is, to some extent, specifications written in large, they are executable. But since they are written at a very high level, if we have a complex specification, converting it into executable code is not going to be easy. So अगर तो आपने specification आपकी executable है, आपने execute करके देख ली, then you see the results whether the specification actually gives you the desired results or not. But if it is not executable, what do? This is where these tools, they come in handy. Important thing here is that what we are saying is that we write these assertions or claims which are in a way redundant. The specification that you have written itself is a claim. It asserts something. You say, okay, assert this thing. So these are the axioms that you have written, and they are supposed to be, what you intend to do. But in order to verify that, and you may want to write a redundant set of assertions which essentially say the same thing, but maybe in a different manner. And then, somehow the two are compared, and then you see whether, you actually get the desired output or not. So the assertions that you're going to write, those assertions are actually going to make the same claim that you have already made when you wrote those specifications, but these are redundant, and they give you this flexibility to be able to argue about the original written specifications and prove their correctness and other properties of those specifications. We will be talking about those provers in more detail later on. But right now, I would like to go back to our large shared language specifications. And, to start with, I would want you to look at specifications, interface specifications written in two different languages for the same specification written in the large shared language. The specification that we have here that we are going to talk about is the same old specification of the table. So I'm not going to go and talk a lot about this specification. We have already seen this specification in the previous lecture. But then I will show you the corresponding specification written in, corresponding interface specification written in two different specification languages. One in C, and the other one is Modula. So the two specification languages, the purpose really is that, we are not going to go into the details of those interface specifications. I would just want you to have a look at it, and I will highlight some of the points. And, the basic purpose of this thing is to show that how these interface specifications, they differ when we move from one programming language to the other, and how closely they are associated with the corresponding programming language. So now let us go back and look at the trait written for the table. So here we have the specification written in the LSL, large shared language, for the table, and then I'll show you the corresponding interface specifications. So once again, it's the same old trait that we saw last time. We have the signature part, the new, which creates table, add, which takes a table index and value and puts that into the table. We have a member function which takes an index in table and tells us whether that index is present or not. Lookup, which takes the table and index and gives us the value at that particular index, and size, which tells us the size of the table that we have. And we have these assertions, and we say for all I1 of type index, V of type value, T of type tab, not I is a member of new. So I cannot be a member of new. It's just a new thing, so there is nothing in it. So I is a member of add, T comma I1 comma V is equal to I is equal to I1, or I is a member of T, the same old kind of formulation that we have seen again and again. Lookup, add T comma I comma V comma I1 is equal to, if I is equal to I1, then V, else lookup T comma I1. Once again, the same kind of recursive formulation, nothing new here. Size new is equal to 0. Size add T comma I comma V is equal to, if I is a member of T, then size T, else size T plus 1. So what we are saying here is that, if I is already present, then we replace the value present at that index with this new value supplied. Otherwise, we add this new tuple into the table, that is the pair of index and value into the table and increment the size by 1, or the size of the table is incremented by 1. So this is the same old specification that we saw earlier on. Now here is a couple of things that you need to note here. Since this is a specification, so this specification does not talk about any of the implementation details. It only says what, not how. It does not talk about the data structures that it has. It does not talk about the algorithms that need to be implemented, or the algorithms that are going to be implemented to carry out the job, and so on and so forth. So implementation details यहाँ पर specification में नहीं है. Those implementation details, they start to come when we start to write interface specification. Interface specification, once again, implementation detail उस level की नहीं आती जो आपके actual program में आएंगी, क्योंकि वहां पर तो आपकी complete implementation होगी. लेकिन implementation detail जो आपकी language specific चीजें हैं, for example the data types, for example those kind of operations, कि आपने यहाँ पर array use करनी है, कि list use करनी है, क्या चीजें हैं, वो चीजें आहिस्ता आहिस्ता आपकी specification में आनी शुरू हो जाएंगी. So as long as your interface specification fulfills the contract or whatever has been claimed or promised in your shared language specification, any implementation is fine. But the point really is that आहिस्ता आहिस्ता जब आप आगे बढ़ते हैं तो आप उसमें फ्लेक्सिबिलिटी आप कम किए जाते हैं, आप उसमें मैटर ज़्यादा ऐड किए जाते हैं. जब आप ज़्यादा इन्फॉर्मेशन आप डालते हैं तो इसका मतलब है आपके पास फ्लेक्सिबिलिटी कम हो गई. नाउ यू आर मूविंग टुवर्ड्स वन पर्टिकुलर इम्प्लीमेंटेशन, and in that particular case the implementation would be C language or modular 2 language or whatever. ये तो पहला स्टेज है, बट उसके साथ साथ डेटा टाइप्स और वो चीज़ें भी इसके बीच में आहिस्ता आहिस्ता आनी शुरू हो जाती हैं जो आप इस्तेमाल करेंगे. So let us look at those specifications. So here is the specification in C, or the interface language for C. We say mutable type table, uses table, table for tab, car for end, car for val, int for int. शुरू में ही हमने ये देखा कि what it is saying is that it is saying that it is going to use the specification that has been developed in the shared language, and there we had certain variables. We had the IND index. Now in this specification we are going to use int for that, because that is what we have in our C language. So the data type for the corresponding abstract data type that we had in the earlier specification, we are going to specify that. So we say in this particular case we are going to use the car, here it is going to be int, here it is going to be some other data type, and so on and so forth. So यहाँ पर concrete data types जो उस specification language की हैं वो आनी शुरू हो गई. Constant int max tab size, table create void ensures result dash is equal to new and fresh result. Boolean table add, table t car I car c modifies t, ensures result is equal to size t hat is less than max tab size or I is a member of t hat, and if result then t dash is equal to add t hat comma I comma c, else t dash is equal to t hat. Once again, if you look at these specifications, this particular जो हमारा एक statement थी, you can very easily make sense out of this thing. Once again, result is what we are going to return from this function. Hat means the value of that particular variable when it entered that function, when the function call was made. Dash or a single quote, when it comes with a variable, it means the value of that variable at the time of returning from the function, and so on and so forth. The rest of the specifications are once again written in an sort of a recursive algebraic format. So यहाँ पर हमने कुछ चीज़ें, कुछ वेरिएबल्स, कुछ नई चीज़ें हमने इंट्रोड्यूस की, कुछ टाइप्स वगैरह हम लेके आए, बट मोस्ट ऑफ द स्पेसिफिकेशन इज स्टिल वेरी मच द ओल्ड स्टाइल अलजेब्राइक स्पेसिफिकेशन दैट वी हैड. सो इसमें हमें बहुत ज़्यादा उसमें चेंज नहीं हुआ. आप इसको ज़रा देखेंगे तो यू कैन मेक सेंस आउट ऑफ दिस थिंग. आई एम नॉट गोइंग टू टॉक अबाउट दिस थिंग बिकॉज दिस इज़ नॉट द पर्पज़ ऑफ दिस डिस्कशन के इसका एक्चुअली मतलब क्या है. बट बड़ी स्ट्रेट फॉरवर्ड सी स्पेसिफिकेशन है. बट पॉइंट हियर वाज दैट द कंक्रीट type information and then the algebraic sort of information, the specification is kind of mixed here. So we have once again car table read table T comma car I requires I is a member of T hat, ensures result is equal to lookup T hat comma I and end of the function. Another important thing to note here is that these interface specifications that we are writing here, these interface specifications, they actually are going to perform the operation in that particular language. So यहाँ पर जो function का नाम आपने दिया है, this will be the name of the method that you will actually going to implement. सो ना सिर्फ आपने यहाँ पर उसको कंक्रीट करना शुरू कर दिया, उसे एब्स्ट्रैक्ट से कंक्रीट की फॉर्म में ले आए, बल्कि यू हैव ऑल्सो स्टार्टेड टू गिव द नेम्स टू द मेथड्स दैट यू विल एक्चुअली गोइंग टू इम्प्लीमेंट एंड in that particular language. And here once again the syntax should correspond and corresponds to the syntax of the programming language or the target implementation language. Now let us look at the specification for the same specification of table in another interface language, and that language is the modular 2 language. So what are the changes? Let us look at it, and then you will see how closely it is related with modular 2 if you know modular 2. But one thing you can see there, that the specification has changed or will change as we move from one interface language to the other interface language. So here is the interface specification in modular. So this language is known as LM3 language. So what we have is we have interface table. Now note that we are using a different keyword here. This less than star traits table, car for int, car for val, integer for int. So we are using the data types that we would use for modular. Type T is of type object. Methods add, and it takes 2 parameters, and it raises some kind of exception. And read takes I as character and it returns a character, and end. So we have the specification of this module. And then we have the procedure create, and then we have the const max table size, which is of type integer, and it is equal to 100. And then we have this exception full. Then we have the body of the module. And the body of the module, once again, we have the axioms written for these different methods, that is add and read and create and so on and so forth. I understand that most of you may not know modular, may not have seen modular. So, I'm not going to go and talk about the details and what is contained inside this language or inside the specification. But, all I can tell you is that if you compare it with the previously written specification in LCL, that is the interface specification for the same object in C or for C language, then you will see the differences. Although the structure and the formulation and those things, they are going to be very, very similar. We are going to write the similar axioms, but the interface languages, they correspond to the particular target language that we have. So in the case of this LM3 specification, the whole structure seems to be a totally different structure. But the reason for that is that it now corresponds to modular language. Modular में you create a module, जिस तरीके से आपकी क्लास होती है, एक sort of आप more or less ये उसी तरह की चीज़ है. So you have the class specification and then you have the class body. Here once again you had the specification where you specified, you declared the methods that would be supported by this specification or this implementation, and then the body, and in the body you had those axioms for all the different methods that we have. So those were the two things that were that I wanted to highlight. The idea really is that once you have written those specifications, for example, if we go back to the specifications written in C, so 3-4 चीजें यहां पर हुई हैं. इसका नाम है इंटरफेस स्पेसिफिकेशन. इंटरफेस का क्या मतलब है? इंटरफेस का मतलब ये है कि ये जो मेथड जो है उसकी सॉर्ट ऑफ प्रोटोटाइप है, और ये दिस इज व्हाट इज बीइंग एक्सपोर्टेड फॉर यूज, and that corresponds to that abstract entity for which we are developing this specification. So it is not just the prototype, not just the header file. उसमें चीजें क्या कुछ आ गई, हमारे पास name of the function आ गया, हमारे पास function के parameters with exact types आ गई, हमारे पास return की type आ गई. So ये सारी चीजें जो आप otherwise आपके function के header में होंगी, they are all there. So this is the interface that we have developed. So जब आप इसका कोड एक्चुअली डेवलप करेंगे तो आप इस इंटरफेस को लेके चलेंगे, इसी इंटरफेस को, बिकॉज दिस नाउ बिकम्स योर हेडर. इस हेडर को आपने लिया और आपने इसके लिए आपने कोड लिख दिया. इसके अंदर जो assertions जो हैं, those assertions obviously they specify what is expected here. मैं ये जो assertions जो हैं, ये जो what is expected here, obviously इसके 2 लेवल्स हैं. एक तो कुछ आपने इस मेथड के अंदर आपने लिख दिया, लेकिन जब आपने इस मेथड के अंदर जो कुछ आपने लिखा है, that has to correspond to the abstract data type from a larger context. For example, in C आप डायरेक्टली एब्स्ट्रैक्ट डेटा टाइप्स आप डिफाइन नहीं कर सकते. C++ में आप एब्स्ट्रैक्ट डेटा टाइप्स आप डिफाइन कर सकते हैं. Then it becomes relatively easier there to talk about those things. Here आपने एक फंक्शन आपने डिफाइन किया, उस फंक्शन को आपका कॉन्टेक्स्ट उस फंक्शन का जो है वो सिर्फ उस फंक्शन तक लिमिटेड है, वो पूरी एब्स्ट्रैक्ट डेटा टाइप तक लिमिटेड नहीं होता. So how do you manage that? The idea is very simple, because now you have written the specifications at multiple layers, multiple levels. जो आपकी शेयर्ड लैंग्वेज में स्पेसिफिकेशन लिखी गई थी, दैट स्पेसिफिकेशन वाज written from an abstract data type point of view. It did not have this implementation bias कि ये पर्टिकुलर लैंग्वेज में मैं एक एब्स्ट्रैक्ट डेटा टाइप में क्लास बना सकता हूं कि नहीं बना सकता, मैं मॉड्यूल बना सकता हूं कि नहीं बना सकता, कैन आई हैव द नोशन ऑफ एन ऑब्जेक्ट देयर और नॉट. In that specification, that concern was not there. I wrote those specifications without that concern. But in the case of the specifications written for that implementation language, the LCL or LM3 language, अब मेरे पास implementation का bias आ गया. जब मेरे पास ये implementation का bias आ गया, for example for C मेरे पास वो पूरे object या abstract data type की notion नहीं थी, but then I inherit a lot of the properties from my specifications written in my earlier specifications जो मैंने LSL में लिखी थी, which were independent of the data type that I had. So उससे क्या मेरे पास मिला कि जो मेरी जो एक function की जो specification थी, which were independent of the other properties of the abstract data types, other attributes which did not take into consideration those attributes, अब वो उसको सारे के यहाँ पर बीच में ले आएगा, because it is based upon the specifications written in LSL. मैं इस गुफ्तगू को आगे बढ़ाऊंगा, ये चीज़ आपको और डिटेल में पेश करूंगा अगले लेक्चर में, क्योंकि मेरे पास इस वक्त ख़त्म हो रहा है, इसलिए मुझे इजाज़त दीजिए। अगले लेक्चर में वी विल इंशाअल्लाह कंटिन्यू दिस डिस्कशन। उस वक्त तक के लिए मुझे आप इजाज़त दीजिए। खुदा हाफिज़ और अस्सलाम वालेकुम।